Now we start with stability analysis in state space part 2. In part 1 we have seen how to determine the eigenvalues and eigenvector, and one point is clear, is that we have seen that eigenvalues plays important role in control system, that is stability, control design. For everything these eigenvalues and eigenvectors are important. Now today's discussion is mainly concerned with how to check the stability of the system when the given system is expressed in a state space form. That is the main objective. So let us see here. In this part 2 we will study introduction to stability, difference between stability in transfer function and state space, and lastly we will see difference between the bounded input, bounded output stability and asymptotic stability. Now about the stability. Normally we say that stability means that when the input is bounded, the output is bounded. That is called a stability. Sometimes we say that when the roots are lying on the left side of the S-plane, the system is stable. If the roots are lying on the right side of the S-plane, system is said to be unstable. Now the stability can be defined in different way. Let us say we have some system. Suppose this is your system. Now if we have applied input to the system, so now we get the output. So normally we find that when the system is stable, whatever input is applied, let us say a steady state or input of 1, output will come along 1. So that means when we apply input in a system, also some internal things, internal states, internal parameter, they also provide some response. So but at steady state all the response will vanish, and remaining is the force response, that is input, force, internal things, and we get the output. So in the output what we want, whatever internal force we applied, that we operate in the output. So I will try to explain the stability in this way. The total response of a system is the sum of natural response and the force response. That means, and I told you that for this system whatever input is applied, that is the force, and whatever thing is provided by the system, that is called natural response. When we studied the differential equation, we generally referred to this response as homogeneous and particular solution respectively. That is called homogeneous and particular solutions. What is natural response? Natural response describes the way the system dissipates or acquire energy. This form or nature of this response is dependent only on the actual system, not on the applied input. That means that a natural response is depend upon the system itself, it does not depend upon the input. On the other hand, the nature of the force response is dependent on the input. Thus for a linear system we can write the total response equal to natural response and force response. For a control system to be useful, the natural response must eventually approaches to 0. That means in other words it should vanish, thus leaving only the force response or some sort of oscillatory response. However, in some system natural response grow without bound rather than diminish to 0 or oscillate. That is sometimes what happen when we apply input, there are natural responses that is will grow and grow simultaneously, moving to a state into infinity, and it is not coming back to the steady state, that is the direction of the force state. So in that case the system becomes unstable. So what is written? However, in some system the natural response grows without bound rather than diminish to 0 or oscillate. So if the natural response is greater than the force response, then system is no longer controlled. This condition is called instability. That means your force response must be greater than the natural response for the stability of the system. If the force response is less, it is okay. If force response, if the natural response is greater than the force, system is unstable. We always want force response should be more than the natural response. Now we can define stability in this way also. A linear time invariant system is stable if the natural response approaches 0 as time approaches to infinity. Unstable, linear time invariant system is unstable if the natural response grows without bound as the time approaches infinity. And third, marginal stable, linear time invariant system is marginally stable if the natural response neither decays nor goes but remains constant or oscillate as time approaches infinity. Now these are different definition of the stability. In a classical studies we have seen the stability with respect to poles. That means we have seen that in the pole lying on the left hand side, this indicates stable. If they are lying on this side, this indicate unstable, but it lies here, that is called a marginally stable. Marginally stable. Now stability in transfer function and state space. Now how to check the stability when in transfer function and the state space? I think you have already seen the how to check the stability in transfer function in a classical part. Now again I am reviewing this part. Suppose if I have written Gs equal to Ns by ds. So N of s, that is Ns is numerator and ds is denominator, and it is written in the most of the textbook that in order to check the stability of this we have to check ds. The question has come into mind, why ds, why not Ns? Ds concerned with the poles and Ns is concerned with 0. So why we are taking care of pole only, not zeros? Our zeros are present in the system, because definitely the zeros are present in the system, but we are concentrating on only pole. Why it is so? This is maybe because you see it, the pole is there. So if you take any equations s raised to n, a1 s raised to n minus 1, a1 s raised to n minus 2 up to n, or if you solve it we get the characteristic equation, that is in terms of s let us say s plus a1, s plus a2, s plus a3. So what will happen at some specific value of s equals to say minus a1, so this part equals to 0 and system will be unstable, whereas about the numerator this will be 0. That means the denominator plays a vital role in case of the stability of the system. Now we can understand this concept this way also. The denominator part, that is say let us say 1 by s is nothing but the 1 by s is nothing but your integrator, and we say s, it is nothing but differentiator. So integrator is generally we call as a low pass filter. Low pass filter means that low frequency, that is at the steady state, and s is the differentiator that is remain in a transient part, and we are concerned with the steady state part. So what will happen at the steady state, the effect of derivative is very less, but the effect of integrator will be remain, because this integrator is a low pass filter. Therefore in that view we can say that in order to check the stability of the system which is in a transfer function form, we have to calculate the roots of the denominator. All the poles of this ds will give you the stability of the system. Now coming to the state space, how to check the stability of the system in state space? So just see here we have x dot equal to ax plus bu, this is the plant, and output equals to y equals to cx plus du. Now in order to check the stability, which element we take? We can take a, b, c, d, on which element your stability depends. So in order to get this point, what we will do, we can write the equation as g of s equal to this transfer function equal to c si minus a inverse b plus d. This equation we have already seen when we convert the given system which is in a state space form into a transfer function domain GS. So GS and this one, so this is GS is the thing but a transfer function and this is the thing but your modern control or state space. So this is a relationship between GS and this one. So what is GS? This GS equal to numerator by denominator, and stability of the GS it depend upon this. Now what we do, now we solve this equation, this C Si minus A inverse B plus D, we have to solve this. So how you solve this? So this Si minus inverse we can write down in terms of adjoint and in terms of determinant. Therefore this equation we can write down as now GS C adjoint of Si minus A divided by the determinant of Si minus A B plus D, and again we solve this, what will get this equation as, we can get it as determinant of Si minus A equal to C adjoint of Si minus A B plus D multiplied by determinant of Si minus A. Now the GS equals to C Si inverse B plus D, and now Si inverse we have written in terms of adjoint plus determinant, and after we have solved it, what we have got? We have got GS, and GS equals to NS and DS. So DS in transfer function is corresponding to this determinant Si minus A. Therefore for DS they are poles, whereas in case of state space it becomes Si minus A. Therefore whenever we check the stability of the system, we are only taking care of A matrix, we never bother about this B matrix, C matrix and D matrix, particularly stability is concerned, as we are easily seen NS DS and this part. So DS is equivalent to Si minus A. So normally we call the determinant of Si minus A, if you solve it we call as eigenvalues, and DS when you solve the characteristic equations we will get the poles of DS. So poles it is in terms of transfer function, and in whenever we say the state space we call as eigenvalue. Now difference between the bounded input, bounded output stability and asymptotic stability. Normally this BIBO word we are use in case of transfer function approach. When input is bounded, your output is definitely bounded. Now about the asymptotic stability, it means if you having x dot equal to x, x dot equals to x, so if you solve it what will get? Dx by dt into Ax of t. Therefore this x dot t, or we can say x of t equals to e raised to at x of 0. This is the state equation. So the more details of these issues we will see later on, but now for time being, because we are to learn what is the difference between BIBO and asymptotic stability, I have written this equation. So x of t, if we solve it we get x of t equals to e raised to at x of 0. Now assume that your time t tending to infinity, and all the eigenvalues of A lying on the left side, that is A is all the elements of are minus. So what happen? X of t tending to 0 at t tending to infinity, that is the stability, that is called, we can say, asymptotic stability. That is for a system x dot equals to x at t tending to infinity, if x of t tending to 0, system is asymptotically stable. I think from this discussion we got one point that BIBO and asymptotic stability are the same things. But can this definition is true for all type of systems? Can we say that for all system is bounded input bounded stable and is also called as asymptotically stable system? Let us see. So now I am taking one example, say this g of s equal to s minus 2 divided by s minus 2 s plus 3. So, this is our system. So, this is 0 and these are poles. So, there are 2 poles and 1 0. Now, definitely when we want to check the stability of the system, we see that s minus 2 in the numerator, s minus 2 denominator, we just cancel it, and after cancellations what we will get? G of s equal to 1 up by s plus 3. So, definitely s minus s plus 3. So, here eigenvalue on the left hand side, that is minus 3. So, this system is stable, because mathematically this thing is true, s minus 2 has been cancelled. Now we try to think from a state space point of view. For that purpose, now we solve this. So, if we solve this, g of s, that is equal to s minus 2 a square plus s minus 6. So, gs we have solved. Now, we want to write this system into state space form. We have seen the different types of form, that is a controllable canonical form, then diagonal form, Jordan form, the various type of forms we have seen, even observer form we have seen. So, now we write this gs in any of the form. Now, we write this gs in terms of state space model. State space model means we want x dot equal to ax plus bu, y equals to cx plus du. The most simple form is a companion form, that is controllable canonical form, where we have taken output as a first variable, remaining variables are the derivative of the output. So, this part we have already seen last time. So, now what we do, whatever things we have learned previously, we want to apply to this problem. Now, the state space model of this plant we can write down as x1 dot x2 dot, because the order of the denominator is 2. So, the order of means number of states we have taken 2, x1 dot x2 dot equal to 0 1 6 minus 1, here x1 x2 plus 0 1 u, and what is the output? It is minus 2 1 into x, 0 into u. Now, we have got A matrix, we have got B matrix, and we have got C matrix and D matrix, A, B, C, D. And previously we have seen that whenever we want to check the stability of the system, when the system is expressed in a state space form, we are taking care of A matrix, we are not taking care of B, C, D. Therefore, here also you will find that here A, B, C, D. So, definitely for checking the stability in state space, I will take care of the A matrix. Therefore, this A equal to 0 1 6 minus 1. Now, we calculate the eigenvalues of this. So, minus lambda I minus A equal to this lambda minus 1 minus 6 lambda plus 1. Now, we determine the determinant of this. Determinant is lambda plus 1 minus 6 equals 0. So, lambda square plus lambda minus 6 equals to 0, and if you solve it, so we will get eigenvalues as lambda 1 equals to 2 equals to minus 3. So, lambda 1 2 lambda 1 minus 3. So, here in transfer function we have cancelled pole and zeros, we have got 1 by s plus 3, and here we have got eigenvalues as lambda 1 equals to 2, lambda 1 equals to minus 3, and we have used all basic concept. Here we are not adding some more additional thing. Based on the basic concept, we have got these results. Here the system is stable, that is in a we have taken a system, this system is stable in transfer function, but the same system we find that it is unstable, because here lambda 1 equals to lambda equals to minus 3. So, why this has happened? Because whatever logic we are applying, whatever be the form, maybe classical and advanced, logic should be same and it should follow the same thing. So this has happened because we have done pole zero cancellations. So you just see here that whenever there is pole zero cancellation is involved, the definition between BIBO and asymptotic stability will never match. They will only match when there is no cancellation. When there is cancellation, it will never match. So here it is written, in the absence of pole zero cancellation, the transfer function poles are same as the eigenvalues of the system. Therefore, the asymptotic stability is equivalent to bounded input, bounded output stability. Now these are some references. Nice, Stephanie. Thank you.